Edexcel Copier, complex numbers 5, complex numbers. Solving z to the n equals 1. Previously, you've solved many quadratic equations. And we know that these quadratic equations will have either two real roots, a repeated real root, or two complex roots, which make a conjugate pair. So visually, if we're talking about a graph, we know that two real roots would be found on a graph looking like that. Repeated roots would be found on a graph looking like that, and complex roots would be found perhaps on a quadratic looking like that. So here we have a quadratic equation in the variable z, which has been solved by completing the square, and we can see that we've got two complex roots, and those complex roots form what's called a conjugate pair. One of them is often referred to as z and the other one as z star. It doesn't matter which one is called z and which one is z star. So in this case I've chosen z is the 1 plus 2i and z star is 1 minus 2i. At some stage you will have also solved cubic equations and seen that they have three roots. Some of these roots may be complex, okay, but the important thing is that every single polynomial equation of degree n will have exactly n roots, some of which may be complex. And if they are complex, the complex roots will occur in a conjugate pair. So some examples of this, if we look at perhaps a cubic example. So here is a cubic curve that has three real distinct roots. Or we could have a cubic curve that has a pair of repeated roots and another distinct real root. So both of these examples are said to have three real roots. Or we could have a cubic curve that does something like this. So there's one real root and there will be a conjugate pair as well. There'll be a complex conjugate pair. And even if we look at quartic equations, so here's an example of a quartic equation doing something like that. There are two distinct real roots, and this one will also have somewhere a conjugate pair of roots. So that's just to emphasize the fact that all polynomials of degree n will have n roots, some of which can be complex. So if we look at z to the n equals 1 in a little bit of detail, even this simple equation z to the n equals 1 will have n roots. One of the roots is obviously going to be z equals 1. I think we can get that by inspection. But there's a few other interesting things to be aware of, and we're going to look at these in a bit more detail in a moment. For example, if n is an even number, there'll also be another root at z equals minus 1. Perhaps not obvious at first is that all the other roots will be complex numbers, and that these complex numbers will spread themselves around on an Argand diagram. So here we have an example of z cubed equals 1 and z to the 4 equals 1, and we're going to look at these examples in a little bit more detail on a GeoGebra file. So at the moment we are looking at the solution to z to the power 1 equals 1, and there's only one solution, which is the real number z equals 1. If we look at z squared equals 1, we can see we're getting two solutions, one at z equals 1 and one at z equals minus 1. N is an even number, so we're getting solutions at 1 and minus 1. It gets a bit more interesting if we now look at z cubed equals 1. We get the obvious solution at z equals 1, but notice the other two solutions form a conjugate pair, and that the three roots are equally spaced out. This is an equilateral triangle, equally spaced out at 2 0.09 radians apart around the unit circle. If we now look at n equals 4, z to the 4 equals 1, we're back to an even power of z, so we've got z is 1, z is minus 1 as you would expect, and the other two answers are forming this regular quadrilateral, this square. And if we go to n equals 5, we form a regular pentagon. There's only one real root there at z equals 1. At z to the 6 equals 1, we get 6 roots, 2 of which are real, z equals 1 and z equals minus 1, but they are equally spaced out around this regular hexagon. And every time we get a regular polygon. Z to the 8 equals 1, we get a regular octagon, etc. So if we quickly revisit z squared equals 1, we can think of this as z squared minus 1 equals 0, which factorises to z plus 1, z minus 1 equals 0, and therefore we get the roots z equals minus 1 and z equals 1 as you would expect, which we can clearly see on the illustration. If we now look at z cubed equals 1, so that's z cubed minus 1 equals 0. You can see if z is 1, then 1 is a solution to this equation. So that means that this can be written as z minus 1 times a quadratic factor. You could find this quadratic factor by long division or inspection. You could also find it using a box method, but we'll find that this quadratic factor is z squared plus z plus 1. So either z is 1 or the quadratic equation is 0. And if we solve this quadratic equation for z, we get the two complex conjugate roots minus 1 plus or minus root 3i over 2, forming this equilateral triangle. You can see the conjugate pair as illustrated. And if we look at z to the 4 equals 1, if we just rearrange this and we treat this as the difference of squares, we've got z squared minus 1, z squared plus 1. So either z squared is 1 or z squared is minus 1. Z could be plus or minus 1, so we're getting two real solutions, one at 1 and minus 1, and that's because n is an even number, or z in this case could be plus or minus I. And we can see the two real solutions, we can see the conjugate pair again, and we can see that it forms this regular square, this regular quadrilateral about the origin. In the next video we're going to be looking at the nth roots of unity.